look at a simplest type of model about an insect outbreak, and we'll analyze it. This is section 3.7. And it's about these things called spruce budworms. They're insects that eat trees, in particular fir trees. Interesting thing about this model is it shows the Cusp Catastrophe. It will end up depending on two parameters. The Cusp Catastrophe imply a discontinuous jump in stable state as you vary a parameter even a little bit. So usually we expect small changes in parameter lead to small changes in state, but that doesn't happen at these points where you jump from a surface like the top surface down to the lower surface. We changed H a little bit and we went from stable state way up there to whoa, far away. And maybe one is desired and one isn't. And then it's not easy to even get back to the good state. We're usually thinking in terms of there's one that's desired, one that's not. This is a budworm. I think it's a moth or something. I don't know. It's an insect that eats fir trees. This is what it does. So these are trees from the Mount Hood forest in Oregon, which I've hiked through on the Pacific Crest Trail. I don't remember anything about budworms, but so an aerial shot of trees that are destroyed by these budworms, or these trees that aren't green. This destroys the wood, destroys the forest. The timescale of the insect is actually pretty fast because they're insects. So they evolve on a pretty fast timescale compared to trees. These trees live for 100, 150 years. If there's a fire, it takes about 10 years to replace a forest. These budworms, their population can grow very quickly. So their density can increase 5-fold in a year. So they have a characteristic timescale of months, whereas the trees have timescales of decades. The parameters will be related to the forest. The timescale of the forest is so slow, you can consider those as constant parameters. And the main thing that we'll look at is the number of budworms. That's just the simplest one-dimensional population model. You could do much more complicated model, a spatiotemporal model, where you look at how many budworms are there in this patch of forest. Maybe you decompose the forest into 10 by 10 meter patches, and then look at how the budworms move and what's the density of trees and so on. But we're going to ignore that level of detail and just say, call it a kind of collective model, a population. So just model the number of budworms in an area. Another picture that kind of motivates the importance of this. This is the spruce budworm population over several decades. So you see the year down there. That orange line is proportional to the number of budworms. And then this chart that's got the trees in the background, that's giving the millions of acres that were destroyed, eaten up. Budworms aren't concerned about eating the tree till it's gone. So they defoliate it. And then you could see when the budworm population was high, there was high deforestation. And if you live in Maine and depend on lumber for your livelihood, this is bad. It could be useful for insight to look at a model. We're not going to try to get something quantitative, more qualitative. What are the different states of this system? There's a spoiler alert in the name itself. There's going to be an outbreak state. What does outbreak even mean? That's what we'll get to. We'll look at a model that was proposed in the late 70s. It'll look like the logistic model. We'll use the following. We'll look at N, that'll be our main variable, capital N, which will vary in time. So this is the number of budworms. The model is that N grows according to a logistic model. So there's capital R times N, 1 minus N, K. And if we left it at that, then we could just go back to the earlier discussion of the logistic model. But there's also PN, predation. That means predators that eat the population of things we're talking about, in this case, budworms. Birds will see the budworms on the tree and eat them. They only start eating them when they see a large enough density. So qualitatively, a plot of PN would look like, so it'll be low until some kind of critical value, and then it kind of asymptotes. So this is qualitatively PN. Where it has the greatest rise, there's some population A, above which birds tend to see these things a lot, and below which they don't. Birds can only eat so much. So unless you have some coupled model of the prey, in this case, the budworm, and the predator, so a predator-prey model, but that's a two-dimensional model, and we'll get to that later. For now, let's just think of this. Just to qualitatively get this shape of curve, we can use the following: b n squared a squared plus n squared. This has the desired shape. It'll asymptote to b in the large n limit. It goes to 0 in the low n limit. And it has this big increase right around A. A and B are both positive parameters. So the full model now is n dot equals Rn 1 minus n over k minus p. No, let me put it in. What we've got here, b n squared a squared plus n squared. So there's the model. We've got, what do we have here? We've got n, which changes with time t, and then we've got parameters r, k, b, a. So we've got four parameters. Now, it's always simpler if you want to analyze the dynamics and what's really important. It's good to non-dimensionalize. And in this case, we would like to non-dimensionalize. If we use the Buckingham Pi theorem, let's talk about non-dimensionalizing this. Non-dimensionalize it. Well, Buckingham Pi, you would look at the units of everything, and because this isn't necessarily physics, this is a biology thing, it's more abstract. There's a dimension to n, and the dimension of this is the number of budworms. So now that's a thing. Call it number of budworms. And then the dimensions of time are time. So we've got two, according to the Buckingham Pi theorem. I think that was it. Was it R equal? Yeah, I think he used R. Or Buckingham Pi, B pi, okay? And then we've got n and t, and then the four parameters. So according to Buckingham Pi, we have k, 6, what it called, I think, parameters for Buckingham Pi, which means we can non-dimensionalize and get a relationship between k minus r, non-dimensional numbers or dimensionless numbers. So that's at least a guide. And one thing we did last time with the bead on the rotating hoop is, well, first we started with the main variable was already non-dimensional. In this case, it isn't. N has dimensions of the number of budworms. It turns out so does A. Dimension of A is also number of budworms. This suggests that we create a variable x, n divided by a, and we could pick a non-dimensional time. Let's say we don't know what it is yet. So there's a non-dimensional time, which will be t divided by some characteristic time scale, capital T. So if we plug and chug, what did we get? We would get 1 over t dx d tau equals r a x 1 minus a x over k minus b x squared 1 plus x squared. I may be missing something here. A is not there, and there may be an a over here. D over a. It looks like we'll get something non-dimensional if we multiply by a times b. So a b t dx d tau equals r a b x 1 minus a x k x squared 1 plus x squared. If we want a over b t to be equal to 1, place t equals a over b. So that would be our time scale to make this thing equal to 1. We'll have this term, which is non-dimensional. If you look at the dimensions, we'll call that r to look like the logistic r. K and a also have the same dimensions. We'll define little k as big K over a. Call this x prime. So prime equals d by d tau. X prime is r x 1 minus x over k minus x squared 1 plus x squared. So this is our equation in a non-dimensionalized form. And notice now, instead of 4 parameters, we only have 2. So this is giving dynamics of non-dimensional x as a function of the non-dimensional time tau with 2 parameters, only 2 parameters. So it's simpler to analyze and will have the same qualitative dynamics as the thing with all of the dimensions. But this only has 2 parameters. So that's good, R and K. And we can even label these. R is like a dimensionless growth rate, and then K is a non-dimensional carrying capacity. How much can the forest allow? We've turned the predation term, there's an implied coefficient of 1. There's no term related to that. It's been rescaled out by non-dimensionalizing. Based on this is of the form x prime equals fx. We could look at what are the fixed points. Hopefully you could see that if you put x equals 0 into that right-hand side, you get 0. So x star equals 0 is a fixed point, which makes physical sense. If the population starts at nothing, it will stay at nothing. Like in my room right now, there are no budworms as far as I know, and it's going to stay that way. We've got x star equals 0 is a fixed point, but what's its stability type? If you go through and analyze it, you'll find that df dx analyzed at x equals 0. It turns out that equals r. This non-dimensional growth rate, how was it defined? It was defined in terms of other things that must always be positive. So maybe I need to say that r is greater than 0, and so is k. So since this is greater than 0, that means from our earlier discussion of linear stability for 1D ODEs, this point is always unstable, which means the population, if it's small, it wants to grow. I mean, we could find out a lot just by plotting this right-hand side, which isn't too hard, but let's be more careful about it. There's other fixed points. If we look at this right-hand side and divide by x, then what are we left with? That's the condition for the other fixed points, assuming there are some, and yeah, there are. I'll just rearrange this so that instead of something minus something equals 0, we'll just set those two equal, and then use the trick from before where we can plot the 2 curves. So we'll plot one and then plot the other and see where the 2 curves intersect. This is over x. Let's plot first the right-hand side. This grows linearly for small x. And for large x, it's going to look like 1 over x, something like that. In between, it's going to do some stuff. That's my crude drawing. And we're just trying to get qualitative things. This other side, we'll plot as blue curves. At x equals 0, it is at the point R, and it goes down in a straight line to 0 at k. Let's say this was k, then it's just a straight line. And you could see it intersects in 1 point. Here's something we could say. For small k, small enough k, and any r, we have 1 fixed point. You can maybe imagine, right, if this went higher and higher and higher, there's still just going to be 1 fixed point. If I were more careful about drawing this curve, I'm going to get something like that. You can have cases where there's 3 fixed points. As things get adjusted, you'll have different numbers of fixed points. But we already know that one of the fixed points is 0. We'll call this point A, this point B, and this point C. Because 0 was an unstable point, this one has to be stable. This one would have to be unstable. And this one has to be stable. This horizontal axis is x. So this point C is what is the undesired state. This is the outbreak, and it's a stable point. This is a small population, manageable population. The terminology is this is the refuge state. This is the unstable point that once the population crosses it, let's say to the right, it's going to outbreak. If it crosses it to the left, it's going to the lower refuge state. For a 1D vector field, systems that look like this, and x is just r, and f is smooth. It's a smooth curve. Can we have 2 fixed points, 2 neighboring fixed points of the same stability type? So can 2 adjacent fixed points have the same stability type? I want you to think of the generic case, which would mean away from bifurcations. Like, so for this to happen, that would mean the vector is pointing that way, and then somehow it's pointing this. Okay, how did that happen? Somewhere you needed to pass through 0, which means anytime you have 2 stable points, there has to be an unstable point in between them. And also if we had 2 unstable points, Remember, we're talking about away from bifurcations. So there's no half stable. If I have the vector pointing away, it's like, well, how did this happen? I can't have this, because that would mean, right, the curve is negative, and then somewhere it had to become positive, and then it had to pass through here. So for well-behaved curves, right, there has to be something. So there would be a stable point there. So that means adjacent fixed points must have alternating stability type. The nice thing about 1D is things are either stable or unstable away from bifurcations. So that's nice. That means if I told you a system had, let's say, 4 fixed points, and I know that this first one is unstable, then you know the stability of the other 3. If this one's unstable, then that means this one must be stable, and then this one is unstable, and this one is stable. So knowing the stability of any one of them tells you the stability of all the rest, as long as you know how many there are.
We were looking for fixed points, and we saw, what are the fixed points? Fixed points. We know one fixed point, and it's unstable. Are there other fixed points? X prime equals 0 at X star equals 0. And then if we can divide through by X, and we'd be left with R1 minus X over K minus X1 plus X squared equals 0. If we set these two equal, then we've got, Y equals R1 minus X for K, and Y equals X over 1 plus X squared. We could plot these two and see where they intersect. Where they intersect would be the points X that satisfy this and therefore provide fixed points. The nice thing about this one, X over X squared, is there's no parameters. This is independent of parameters. So we could just plot this. The other one does depend on parameters. And I made an argument about how you would kind of sketch X, 1 over X squared. I've now cheated, and I'm just going to show you the plot. There is a plot of 1 over X squared. Y equals X, 1 over X squared. If we want, I can plot Y, and then this is the X-axis. And they're not equal because it doesn't highlight what I want. So this goes out, X goes from 0 to 30, and Y goes from 0 to 0.5. Now, the nice thing about the other curve was that it intersects the Y-axis in R and intersects the X-axis in K. So we said for small enough K and all values of R, there's only going to be one intersection. So that was just one other point. For large enough values of K, so let me put K, it's just a straight line that connects R and K. So here's K. Suppose K is over there. For small r, small enough, here's a straight line. The curves only intersect, and it's hard to see, right? Because I plotted this to scale. Over here, the two curves intersect just in one point that's close to x equals 0. Let's say I start increasing r. So remember, I've got two knobs in my parameter space. Let's keep k fixed and increase r. As we increase r, the line will rotate, and it'll rotate up till it just barely touches. Maybe I'll plot this as a dashed line. Here's another value of r. And at this point, there's a tangential intersection of the two curves here. There's also one here that's not tangential, but there's a tangential intersection there. If I go beyond that, then it'll pivot up even higher. Let me go maybe up here. It's kind of hard to draw straight lines. Now we've got 3 points of intersection. Now let's take that case. We'll call these points C, this one, B, and then this one that's closest to 0 but not 0 is A. If we were to plot the vector field, x prime versus x, we have the point 0, point A, and I'm just sort of sketching where they are, just making sure I've got them. So this is 0, there's A, here's B, and here's C. Well, we know the first point is unstable, which means the second point has to be stable. So we'll make that a filled circle, which means this point B is also unstable, and point C is stable. Remember, because they have to alternate stability, which means the way that my plot looks, if I were to plot x prime, I'll get something like this. Remember, it has to be smooth. So and then I could plot kind of the vectors, where things going. You might say, well, why didn't you just plot this from the beginning? I could have, but we have this nice argument that there's this curve x, 1 over x squared. And then as we vary the parameters, it just sort of pivots this straight line. And there's this critical point. So for a particular value, maybe we'll call that r star for a given k, we have this tangential intersection. And beyond that, 2 new fixed points show up of alternating stability type. So that would be a saddle node bifurcation. So at this point, we have a saddle node bifurcation. And if you look at this vector field, remember what x was proportional to? X is proportional to the number of budworms, these pests that eat fir trees in the forest. So there's a stable point that has a large number, and that's why this point C has been called the outbreak state. And this other point, probably for ecological reasons that I do not know, is called the refuge stable point. And then this point B in the middle kind of separates those two. So if you have a population that is to the right of B, it's going to go towards the outbreak. If it's to the left of B, it's going to go towards refuge. So maybe this is a manageable population of budworms. And of course, if you start with anything above 0 budworms, it's going to increase to A, to at least this refuge. If possible, you want to avoid the outbreak state. And maybe you do that by K and R represented things related to growth and the capacity, carrying capacity of this budworm population. So maybe those could be controlled somehow. What I want to show is that we can plot in the parameter space of R versus K the number of fixed points. Below this saddle node bifurcation, there's only 2 fixed points. And above that, there is more than 2. So now let's plot the parameter space. And I think this was called a stability diagram. I'm just going to sketch it. If we plot the points, so for small enough k, there's only 1 point. Actually, there are 2 fixed points. We're only talking about the number of fixed points other than 0. So 1 fixed point, meaning other than 0. But for large enough k, there's this strange thing that happens. For large enough k, if you have a large value of r, if we pivot to large enough, let me put this up here. There's only 1 intersection, and it's just the outbreak state. That is important. That's what I wanted to summarize here. There's 1 fixed point, and it's called the outbreak. Seems pretty bad. Down here, there's still 1 fixed point, and it's the refuge. And in between, there are 3 fixed points. Hopefully you could see that. If I do the other dashed line that's tangent to this top, the 2 dashed lines correspond to the 2 saddle node bifurcations that are occurring. And that's what correspond to these 2 lines. Maybe I'll do like this and like this. So if I'll highlight these in purple, those are the lines of the saddle node bifurcation plotted on the parameter space. So we could also show this as, I'm still plotting R versus K, but I'll plot it in a way that maybe makes more sense. Up here in this part of parameter space, the only stable point is outbreak. So you'll only get outbreak. What does that mean? That means it's like A and B merge in this green curve up here, and we're just left with, something like this, which is bad. You don't want that. And for small enough values of R, all you have is refuge. And then in between, we might say there's bistability. There are 2 stable states. So this is the bistable situation. If we plot this now where we've got the X location of the fixed point and then K and R, so that 3-dimensional view, then we will see a thing that looks like the Cusp Catastrophe. There it is. So this is just a sketch, right? And down here in the bottom, this is sort of showing the same thing that we see for the plot in the upper right? This is showing K versus R and the 2 lines of saddle node bifurcations. The problem here would be if you start with a large value of K, but a small value of R, then this thing might slowly, and let's say R increases. R was the rate the reproductive rate of the budworms. So suppose those increase for some reason. Then you go to this situation where there's two stable states. And then if you cross this line up here, this thing, then you go up to this outbreak situation and you're stuck with outbreak. And then even if you try to reverse course, let me plot that blue, you're stuck with outbreak till you get to another value and then you drop back down. So it's the cusp catastrophe. If you really wanted to know how to plot those two curves that I'm showing and I've highlighted here, you could do them as a parametric plot and you could go through those details if you want, but just knowing that they're there is important enough. So that's what I wanted to say about that example, making a connection with this cusp catastrophe thing.